Hello, once again. My name is Róża Okoń. I am an undergraduate student of chemistry and physics from the University of Warsaw, but scientifically I work with the research group from Wrocław University of Science and Technology in Poland, under the supervision of Dr. Rafał Szabla. And today I would like to tell you something about ultraviolet, shortly UV radiation, being a selection factor in early prebiotic molecular evolution. So let me begin by explaining why we should consider ultraviolet radiation at all. Why it can be important in the context of origins of life. So it is quite obvious for us that then when we think about how could life originated, we have to have on our minds the unchanging laws of chemistry and physics. But what can be less obvious is that there are also some planetary and geochemical conditions which have been evolving over the millennia, and they have been very different back in the prebiotic era than they are now. So one of such conditions which have been remarkably reshaped since the dawn of life is ultraviolet radiation and its abundance on Earth. And there are two major reasons of that. First of them is activity of sun, which have been concluded to be significantly higher back in the prebiotic era than it is now. And the second factor is ozone layer, which is a layer of accumulated in stratosphere ozone, or free molecule containing free atoms of oxygen, which today shield out a significant part of ultraviolet radiation from sunlight trying to reach our planet. But what is important to have in mind when we are considering prebiotic chemistry and conditions on the young Earth is that to form ozone molecules, we do need molecular oxygen, O2, which is composed of two atoms of oxygen. And today, again, it is very common in atmosphere. We need it to breathe, but back in the prebiotic era, it wasn't present at all in the reducing atmosphere of Earth before the origins of life, and it is just one of the products of metabolic processes of some simple life forms like algae or cyanobacteria. So from that facts, we can conclude that UV shielding ozone layer has been formed after the emergence of life. And taking this fact together with the fact about sun activity, which was higher back then, we can come to the conclusion that UV was far more abundant on the young Earth than it is now. And one of the factors which distinguish ultraviolet radiation from different components of solar radiation is its high energy, which is higher than, for example, energy of visible light. And some molecules, referred as chromophores, can interact with ultraviolet radiation and absorb this high energy in the process called excitation. And although most molecules before such excitation, in the situation called ground state, when molecules do not have any excess energy of such origin as excitation, in such ground states, for most molecules, all the electrons are paired, are somehow we can think about like having very like the same energy and being somehow connected. But after the excitation, which is very closely related to the rise of the energy of molecule, we observe separation of paired electrons, resulting in a molecule in excited state, which is often very reactive, very unstable, and very likely to undergo a variety of different chemical transformations. And when you think about it, we can conclude quite naturally then that if the lifetime of such excited state is long, meaning that molecule spent a lot of time having unpaired electrons and being such highly reactive, the chance for undergoing different processes is becoming higher and higher. And by different processes, I mean, for example, different biomolecular chemical transformations. For example, with the molecules from the environment, with the solvent molecules. And these are processes which are sometimes occurring in not really controlled way, and they can lead to even the degradation of the molecule, because it can react in very unpredictable way. But on the other hand, some molecules do not have to live for a long time in excited state, but they can have a possibility for very rapid decay by undergoing some very selective chemical transformations. And considering these two scenarios, we can think about UV light as about a factor which can play two very distinct roles. At first, it can be a selection factor, which can lead to the photodegradation of molecules which are not very photostable, which do have very long excited state lifetime and can undergo many undesirable chemical transformations. But on the other hand, the same factor, UV light, can help a molecule to undergo some processes which are normally inaccessible in dark chemistry, but which can be very useful for us, for example, in planning or like proposing some prebiotically plausible synthesis of, for example, biomolecular building blocks for simpler compounds. And such idea is quite old in the field of prebiotic chemistry, because it dates back to the turn of 60s and 70s of the last century. And from this time, obviously we have done significant progress in proposing many prebiotically plausible synthesis of such biomolecular building blocks, like for example nucleosides. But UV radiation is often still very key factor determining many important stages of reactions included in such reaction schemes to take place. And here on the right-hand side, you can see a fragment of the scheme from a very recent paper from 2020 by Zhu et al. And it is a scheme of probiotic synthesis of nucleosides. Okay, and although you can think about UV being a very important factor, just as one of the many hypotheses we can find in prebiotic chemistry, like for example, life emerging in a deep ocean, there are some important premises making this theory very plausible. And first and probably the crucial is that the biologically relevant molecules are shown to be really photostable comparatively to the very similar molecules which do not perform any biological function. And it could lead to the conclusion that UV could eliminate it from the environment of the young Earth, these non-biological compounds which were less photostable, and it could lead to the selection of biological compounds, these more photostable for actual biological building blocks. And here on this scheme, you can see a comparison of lifetimes, because as I said on the previous slide, lifetime of the excited state is very closely related to photostability. When we have a long lifetime of a molecule, there is a bigger chance for undergoing some not very well controlled processes and to undergo photodestruction. So in the case of biological nucleobases, we can see that lifetimes are often about few picoseconds, where picosecond is 10 to the negative 12 of a second, which means it is a millionth of a second. While for non-biological nucleobases, the compounds which are very chemically similar, but they do not perform any biological function, this lifetime is more than 1,000 times longer, about few nanoseconds. And this suggests that the differences in lifetimes tell us that there is significant difference in photostability of these biological and non-biological compounds. And it suggests that biological compounds could have a really long history of interaction with UV, and that it could be a selection factor indeed. So having this on our minds, together with my group from Wrocław University of Science and Technology, we took a closer look for a synthesis proposed by Zhu et al. In 2020 in a scheme which I shown you 2 slides ago, I guess, and we asked the question about the products of this synthesis which are forming here, because one of the nucleosides which are being formed in the synthesis, specifically adenosine, is formed not only in the form of biological compound, not only in the specific form which is DNA building block, but it is also formed in the second isomer, which do not perform any biological function. On the right-hand side, you can see the formula of these 2 compounds. They are very similar, but you can see some structural differences. These are just 2 different compounds, and one of them, the one on the top, and 9-adenosine, is biologically very important molecule because it is building block of DNA, and the one on the bottom, and 7-adenosine, do not perform any biological function. Nevertheless, both of them are being formed in the synthesis proposed in Nature in 2020, and there is no clear chemical mechanism in the synthesis itself which could lead to the selection of one of these compounds over another. So together with my team, we asked a question whether ultraviolet radiation could be a factor which could lead to the selection of a 9-adenosine over its non-biological isomer. And some preliminary computational results reveal that there are a significant difference in photostability of these 2 compounds. That a 9-adenosine, that biological one, can be really more photostable than a 7-adenosine, the non-biological one, which could lead to the could be a strong premise for our hypothesis. And what do you see on this slide? These are plots of energy of molecule changing through some chemical reaction, photochemical reaction, precisely speaking, which allows the system to relax its excess energy after excitation by returning to the ground state. So the situation in the left side of each plot is some starting point just after the excitation. The line on top is representing the excited state, while the bottom one is representing ground state in both plots. And you can see that both of the molecules, both 9 and 7-adenosine, do have such reaction, which allows for obtaining some geometry, which allows for relaxation, the excess energy. But the crucial difference between these two plots and these two molecules is the topography of these plots. Because when we examine them, we can see that in the case of N9-adenosine, this reaction is really barrierless, meaning there is no activation energy molecule need to reach to get from the starting geometry just after excitation to the geometry corresponding to getting back to the ground state. Therefore, N9, biological isomer, can very quickly come from the starting geometry to this corresponding to ground state, and the lifetime for excited state could be very short because there is a really fast way to back to the ground state. And the case of N7, non-biological adenosine, is quite opposite. Here we observe a deep minimum on the plot of energy, and we observe also an energy barrier which molecule have to reach to be able to obtain geometry needed to back to the ground state. So the lifetime, the time needed for such transformation from initial geometry just after the excitation to reaching this final geometry is significantly longer, and therefore lifetime of such excited state will be also meaningfully longer than in case of this biological molecule, which is N9-adenosine. And this comparison of lifetimes can also lead us to conclusions about photostability, because it is some important premise that indeed N9-adenosine will be much more photostable, and it could be working that way, in a way in which we are thinking could work, that UV radiation could just eliminate less stable N7-adenosine from the early Earth environment. And whilst such simple computational simulations can provide us with some qualitative information about lifetimes and photostability, more effort is needed to obtain some quantitative information. And I managed to do that by employing time-resolved transient absorption spectroscopy, which allows us for tracking the ultra-fast photodynamics of considered systems in real time. And although these experimental results are yet to be compared with my further calculations, including quantum chemistry, we can already confirm that biological adenosine, this biological N9-adenosine isomer, is indeed more photostable than its non-biological isomer, which makes our hypothesis of a role of ultraviolet radiation in this selection more plausible. And from here, I would like to sincerely thank the group of my exceptional supervisor, Dr. Rafał Szabla, from Wrocław University of Science and Technology, as well as the group of Professor Dimitar Saselov from Harvard University for their hospitality and openness for discussions. Thank you so much, and I'm happy to answer your questions. Okay, and I see a question on the chat from Christian Latos. Could UV have been a factor in selecting other molecules than adenosine? And if yes, which ones? Yes, generally we can think about ultraviolet radiation as a selection factor for many, if not all, biologically relevant molecules, because all the molecules were if the ultraviolet radiation was really abundant on the early Earth, it was interacting with all molecules, causing elimination of these not very photostable ones. So the best selection, example for that probably are just other nucleosides. Next to adenine, we have as well. We have uracil, we have cytidine. These are nucleobases, but maybe I can share a slide for slides for one more second, because I have something which can help me answering that question. Okay, I have now some problems with sharing. Okay, maybe I will manage to do that without slides. Yes, we have, for example, different nucleobases, like except of adenine, which is a component of adenosine. We have also cytidine, we have uracil, we have thymine, and we have guanine. And all of these molecules are very photostable in comparison to the molecules which are very similar to them, but do have some differences and do not perform any biological function. And this fact suggests that the history of interactions of these molecules with UV light can be really long, and that UV could play a role in selection of these molecules from these non-biological ones because they were photostable. So I hope it answers your question. And we already are out of time. So thank you so much for listening to my presentation and for attending this probiotic chemistry session.